Hi, my name is Bob Cavezza, and I'm presenting my final project for CSCI E-92, the operating systems class, and my final project is called the Bob OS operating system. And the Bob OS operating system was built for the NXP Freescale K70 Tower computer system. It features an in-memory file system and device-independent I/O, among other things. Most of the operating system is POSIX-like in nature, and the special feature that I built for this operating system is an implementation of pipes. For memory allocation, we have two commands that we use, and they're similar to malloc and free in POSIX, and it's mymalloc and myfree. And we also use a first fit algorithm for allocating memory. And the main reasons we use this were that it's one of the rare instances where one of the simplest algorithms is also the most efficient. Device-independent I/O is really important because it allows systems programmers to be able to implement other devices that will interact with your operating system by using a common interface. And here's the interface we use in Bob OS. myfopen, myfputc, myfgetc, and myfclose. Devices currently supported in the operating system are an LCD screen, push buttons, a thermistor, a potentiometer, LED lights, UART for serial communication, and touch sensors. Here's a list of the supervisor calls that we currently support. Supervisor calls are important because it allows system programmers to access key parts that can only occur in the kernel mode. It allows us to do this by keeping access restricted, by allowing them functions to get certain things that they would need to retrieve from kernel mode. The three main timers we use are one, the PDB timer, which we use for a few miscellaneous functions like flashing of LED lights. The systic timer is used for many of our multi-programming functionality, like keeping track of the number of nanoseconds for yields and when the quantum ends in scheduling. And the flex timer is used for keeping system time. And here's a list of the interrupts and the interrupt levels that we use. Here is a snapshot of the interrupt vector table. And here are the specific interrupt levels for Bob OS. 3 and the lower numbers are higher priority. 3 is the flex timer, which is used for system time. 7 is the UART interrupt for serial communication. 12, the PDB timer. 14, the systic timer and PendSB interrupt for yields and quantum endings. And finally, supervisor calls with the lowest priority. Here's a list of shell commands currently supported in Bob OS, and let's take a look at them briefly. All right, I am going to turn on the operating system in debug mode. And let's go over to the screen, and I'm going to type in ls, where you can see that each of our devices are stored as files. I'm then going to run the date command, where you see 10 seconds has elapsed since we started. I'm going to type open stream, so you can see that with every process, we have the standard streams 0 through 2, and PS will show that we have the 0 PID, which is this main shell process running. If I type it again, you will see that time has elapsed with this running process, but time has not elapsed with the blocked process that I created just to show blocking capabilities at boot. If you see date again, you see that time has elapsed. I can create a file, let's call it myfile.txt. You will now see that OpenStreams is not yet open until I open myfile.txt with write privileges. Now OpenStream should have a third OpenStream. I can fputc the number 3. Now I will fopen myfile.txt and write. mode, you can see that there is an additional, and now if I fget C file descriptor 4, the number 3 shows up as expected. All right, one more thing. I just want to show the memory map, which is a map of memory utilized and memory free. Once again, this is using the first fit algorithm. All right, let's go back to the slides. For multi-programming, we use a round-robin scheduler. We use this by storing our process control blocks in a linked list. That's a circular linked list. The quantum time is, I believe, 40 milliseconds. And after that time, we pull off the stack and schedule the next ready to be run process. And with our multi-program, we also, besides spawn, which I mentioned earlier, we also use wait, kill, block, and wait at different times. Now I'm going to demo the multitask command. And multitask is a good showing of our multi-programming capabilities. This command spawns 3 processes at one time. One is a flashing LED light, which flashes once each second. Another is a push button to UART command, which will write text when the push button is pressed. And the third is the UART to LCD command, which will copy text typed from the UART onto the LCD screen. Now we are going to test the multitask command. Notice no lights are blinking on the machine. I type multitask, and now every second lights are blinking. If I type text on the keyboard, they appear on the screen as well on the LCD. The light is still blinking. And when I press the push button, that will actually display here. Okay, now I am going to demo the grep command. And this is a pseudo implementation of the full grep. Basically, this is acting like a string finder with no regular expression support. So if we go back to the operating system, I can type grep blue here, and this would now allow a user to type something here. We can say this is red. It does not copy it again, but if we type this is blue and hit enter, this is blue is actually there twice because grep found it. And you're going to see why we use grep, why I implemented grep in our implementation of pipes, which brings us to pipes. Okay, we implemented pipes by use of a special file type, the pipe file. And it acts as a buffer with simultaneous reading and writing with blocking I/O. And it allows for graceful exits. Some of the variables here that we put on each file is pipe, and also whether each stream, the inputs and outputs are open, and the PIDs of the readers and writers. And this helps with graceful exits and also knowing the PIDs to wake and block when the buffer is full or empty. And on the shell side, the basic logic is that we find commands typed in with a pipe, and then we intercept that command. Then we create each, we parse the text to create each command, and we spawn those processes, then block them. Then we iterate through, and we create a pipe for each 2 commands that should be piped together here. As you can see visually, and once they're piped together, then we go through and wake those processes. So let's look at a demo of pipes. So here you can see the files that we currently have, and if we want to look for just the device files, we would do ls pipe grep dev. If we want to look at maybe just the touch centers, we can do ls grep dev pipe grep touch. And this does multiple pipes here, and we support, I believe, up to 32 different pipes. And let's go all the way and do 3 pipes here and get just the touch sensor with 2. There you go. And to finish this off, where the current state of the operating system is that all problem sets have been completed. The additional extra feature for problem set 6 is almost complete with the blocking I/O for the UART. That should be finished by Friday. The special feature is complete with pipes and grep. And in general, I need a little more work on handling the non-happy path pipe commands. I think any good operating system should not break, and currently there are some scenarios with pipes. If you type in incorrect information and bad data, the operating system will crash. Thank you.